Okay, hello everyone, welcome back. What I want to do now is start just again with an introduction to elliptic curves. So here's an introduction about elliptic curves and especially why elliptic curves. We already, if you've seen the video of the first video on the playlist, you've already seen some of this introduction, but so why elliptic curves is, in my opinion, is because it's the next logical step in the theory of Diaphantine equations. So if you're interested in what we call arithmetic geometry, which for me, arithmetic geometry is the study of Diaphantine equations, Diaphantine after Diaphantine equations after Diophantus, who was the first, perhaps one of the first Greek mathematicians that started a systematic study of Diaphantine equations. So what is a Diaphantine equation? A Diaphantine equation is any equation of this form. So you take a polynomial equation, f x1, x2, xn, so some polynomial in over the integers in n variables, and I'm going to call that z with x bar for all the coordinates. And then we are interested in one equation, so such as f of x equals 0, and we're trying to find all the solutions to such an equation. So we are interested in finding out, are there solutions over solutions to f of x equals 0 over the integers, perhaps over the rationals, over other fields, other number fields, and so on. But mostly we're interested in the integers and the rationals, first of all. And if so, if there are any, if so, can we find any and can we find all? And in fact, so as I mentioned in that other video, of the problems that Hilbert proposed in the year 1900 in the ICM, Hilbert problem number 10, is there an algorithm that that will, given any Diaphantine equation, will tell you if there is an integer solution or not? This was surprisingly answered negatively by Matyasevich in the 70s. Said no, and this is over the integer, so there is no algorithm that would give you an integer solution in general, but of course there is algorithms that will give you solutions for specific types of Diaphantine equations. So so if you start with Diaphantine equations, so solving Diaphantine equations by their complexity, then you can start first by complexity. You would start with one variable, Diaphantine equations. So you're looking for solutions of polynomial equations, f of x equals 0, polynomial. And then you can show that if you have an equation such as an x to the n plus plus an minus 1, plus a2x squared plus a1x plus a0 equals 0 with ai's being integers. Let's say an is not 0, and suppose that we have an integer, or a rational rather, root is a root, then S divides a0 and T divides an. This is one of the problems in the homework set. Okay, just for you to remind yourself how to do that. But that gives you an algorithm of how to solve all those Diaphantine equations in one variable. So now we move on to two variables and degree 1. So those are lines in the plane. So those are lines ax plus by equals z with a, b, c, let's say non-zero integers. Then the theorem here is that there is an integral point if and only if the GCD of A and B divides C. And that is basically the content of like the very first part of an elementary number theory course, where you develop the theory of divisibility and you develop the theory of GCDs. And if you look at it from the point of view of a Diaphantine equation, or with the point of arithmetic geometry, what you're doing is trying to find out whether there are integral points on a line. And then out of this, actually, you can, from the proof of this, you can construct all the points on the line. All right. So what about if we do two variables on degree 2? Then all of a sudden you are in the territory of let's assume that this is going to be some smooth curve. I'll do that here. So now I have what is a conic, so something like ax squared plus bxy plus c y squared plus d x plus f y plus g equals 0 with all the coefficients in the integers. And now all of a sudden it's a lot more difficult to find solutions. A big theorem that probably Legendre needs some credit for, and also Hasse-Minkowski, says that, well, that we're going to assume, as I said, that this is a smooth conic. It says that C over the rationals has solutions, if and only if there are solutions over the reals, and there are solutions over the p-adics for every p, for all prime p. So being the reals and the p-adics being the completions of Q with respect to all the possible metrics of the rationals, what this is typically called is the, well, I wrote it, is usually the local to global, but this side is global to local principle, or the Hasse-Minkowski principle, that if there are, well, one direction is clear that if there are global solutions, if there are solutions over the rationals, then because R and QP are completions, then there are solutions over the reals, or there are solutions over the p-adics. The other direction is what the interesting part of the theorem is, that if there are local solutions, if there are real and p-adic solutions, then there is a global solution. There's a solution over the rational numbers. So this is a very interesting theorem that tells you that how to determine if there is a solution. You can do this once you know that there is a solution. Then you can use other methods to first bring the conic into a canonical form, like an ellipse, a hyperbola, or a parabola, and then use some methods from elementary number theory, such as continued fractions and so on, to find the points in there. Now, if you look from the point of geometry, we'll talk about the genus in a moment. Lines and conics are what we say are curves of genus 0. Okay, so when we go up a level now of difficulty, when we go 2 variables on degree 3, it turns out that if you have a smooth in the projective space, a smooth curve that is of degree 3, then this is going to be of genus 1. Okay, so when now if I have my my curve is now given by something like ax cubed plus bx squared y plus ... then if I assume that this is going to be projectively a smooth curve, it turns out this is going to be genus 1. The global to local principle now is broken, so it turns out that the local to global principle fails, and that is the main problem we are going to encounter with elliptic curves, with genus 1 curves, is that the local to global principle fails, and you have, for example, an example of Sommer, where you have a curve such as 3x cubed plus 4y cubed plus 5z cubed equals 0, has solutions over R and over QP, all primes P, but no rational solutions. Okay, so so from that point of view, then you see that that failure of the local to global principle in these cubic forms is going to cause a lot of trouble. And then what we're going to do at the very end of the class is build up some theory, such as the Sommer and Shaw groups, that will measure the failure of the local to global principle. By the way, there is, let me just add a reference here, the paper of Sommer where this appears. So Sommer talked about this, and the Diaphantine equation, just abbreviate the Diaphantine equation, ax cubed plus by cubed plus cz cubed equals 0 in Acta Arithmetica. 85 in 1951, 203 to 362. Okay. Now, what happens if I go above this? So if I continue like this, so it turns out that genus 1, we will see that just by requiring genus 1 without even requiring the degree, I will be able to put my genus 1 curves in terms of a cubic form. So now the level of difficulty of the arithmetic of curves is actually dictated by the genus. So what happens if I go to higher genus curves? So now a curve, so something like y squared equals a quintic or some things like this. Those will be curves of higher genus. And what happens is that it is actually very difficult to compute the rational points on these curves, but in a sense, they're actually slightly easier by a theorem of faulting. So theorem, this used to be the Mordell conjecture. Now known as Faulting's theorem. So if C, let's say over a number field, let's say over Q, is a curve of genus bigger than 1, then the rational points is a finite set. Okay. It turns out then that over higher genus, there's always just a finite number of rational points, but in genus 0 and 1, you can have infinitely many points. It turns out that in genus 0, you either have no rational points, so you either have no rational points on a curve of genus 0, for example, on x squared plus y squared equals -1, you do not have any rational points. Or if you do have rational points, then you have infinitely many rational points. Okay, or infinitely many rational points. But in on elliptic curves, you have all the flavors. You can have no rational points. No, elliptic curve. On a genus 1 curve, you can have no Q points. You can have finitely many Q points, or you can have infinitely many Q points. So you can have all these possibilities of no rational points, finitely many rational points, or infinitely many rational points in a genus 1 curve. Over genus 2 and above, it's always a finite set. Okay. So from another point of view, elliptic curves come up in all sorts of different ways. I have some examples on the in the homework. So, for example, I need to do some examples of Diaphantine equations. And also sort of by genus of the Diaphantine equation. One of the problems that is some, just for historical reasons, on genus 0 or on lines, an interesting problem is actually something called the 100 fowls problem, which says that so one rooster is worth 5 kian. 1 hen is 3 kian, and 3 chicks is 1 kian. If we bought 100 fowls with 100 kian, how many roosters, hens, and chicks did we buy? So this leads to finding z points on a line. This is a very famous problem because it dates to something like the 5th century of the Common Era or something like that. So some almost 2,000-year-old problem that leads to some very basic number theory. So that's one of the problems I'm suggesting in the set, so I'm not going to tell you more about it. I'm also suggesting another problem, that is find all the points Q points on the conic x squared minus 3xy plus y squared equals 5. So to do that, what one does is do a parametrization. And to do that, what you do is some stereographic projection. So if you have a conic, and you have to find one point first, but once you have 1 point, then you can trace lines. And when you trace a line with a rational slope, then you're going to find more points. And when you trace through all the possible slopes, you can find all the points. You can also prove, actually, that if you have a conic, this construction actually gives you all the points on a conic. But I'm just giving you a practical example to try your hands on finding all the rational points on a conic. Now, finding the rational points, actually, it's the easy part. But finding the integral points is the hard part. So let me show you one example that is also in the problem set, which is the following. So triangular numbers are those numbers that can be arranged in an equilateral triangular form. So this is a triangular number. 3 is a triangular number. 6 is a triangular number, and so on. Square numbers, of course, you know what those are, but they are numbers that can be arranged, again, in a square form. So 1, 4, 9 are square numbers. And the question that I'm proposing is find at least 5 square triangular, what did I call them? Square triangular numbers. So numbers that are both triangular and square at the same time. And of course, you can Google this and find them very easily, but the challenge is for you to find them yourself. What equation do you have to solve? And then you'll see that what you have to solve is you're finding points on a conic, but this time you're finding integral points on the conic. So the interesting part is that when you have a conic such as this, it's easy to find all the rational points by a parametric solution. But once you look at the parametric solution, it's not obvious how to find which of those are integral points, if any. So the same thing happens here, that you can find a conic, and then finding the integral points, that's the hard part. So there is 2 parts to this: find at least 5, and then also find. Can you characterize? Can you characterize all the integral, all the, actually just call them the square triangular numbers? So is there a formula for them? Is there a way to construct them? How would you characterize a family where they are all there, and it's some sort of algorithmic family where you can find them all? Okay, so it's a little bit of a fun open-ended problem. What kind of parameterization, what kind of description you can come up with. Last, for today, let me just say, I'm also, one of the problems is actually proving part of Hensel's example. So proving, so if you have a familiarity with the p-adics, proving a piece of the Selmer example. But let me finish with another problem here, which is find all sets of 3 consecutive integers whose product is a perfect square. So this should lead to finding points on an elliptic curve. Okay, so if you find an equation for that problem, that will lead you to an elliptic curve. And this particular problem, well, if you find an elementary solution, then great. Otherwise, we're going to have to wait until we develop more theory to start finding points on that. Let me just say what the equation for that would be. So if you write x is the first integer, and you multiply x by x plus 1 times x plus 2, you're looking for that to be a square. So that y squared equals a cubic polynomial. That is a cubic equation, and this will be an example of an elliptic curve. By the way, you can do a little bit better in terms of the model for this, that if you start with the x being the number in the middle of the 3 that you are multiplying, then you have x minus 1 times x plus 1 equals y squared, and then that will be x cubed minus x equals y squared. So that will be an elliptic curve that will come up a bunch of times, and then if you can come up with an elementary argument to find all the integral points on this elliptic curve, then you've solved the problem. Otherwise, we'll wait a little bit to come up with better methods to treat elliptic curves. And this is one elliptic curve that we can completely identify what all the points on the elliptic curve are. All right, so I think I'll stop here for today. And next time, I will do yet one more introduction to elliptic curves from the point of view of algebraic number theory. So I will actually be doing a comparison between algebraic number theory and elliptic curves, and in which sense elliptic curves is sort of like a 2-dimensional algebraic number theory, or a natural continuation of algebraic number theory because of the striking similarities between the arithmetic of number fields and the arithmetic of elliptic curves. So that will be next time. All right, and I'm going to stop the video. Goodbye.